Jan is going to be showing us BASO4 framework for data analysis, a plugin for IDA. So, warm round of applause, please.
All right, how's everyone doing? It's cold out. Does anyone want me to do the other talk instead? I can do the black hat talk. No? All right. Damn you guys. Okay, so this is BASO4, barium sulfate. Does anyone know what barium sulfate is? Hands up. It's, no. Yeah, that's it. So it's radio. It shows up in the pictures when they take x-rays. So they give it to you either as an enema or you take it through the mouth. And then you get that. So that's a cat with a barium enema. It shows what problems are like inside with the intestines or leaks or any bad things. So there's a little bit of a metaphor there. Can anyone guess? All right. So I'm Dion. I write programs for a living. I'm a programmer. I don't really do this hacking stuff for money yet. And I write a lot of code. So I kind of get ideas about how the code will be organized in the commercial programs that I look at. And one thing that I'm always really looking for are new tools to understand those programs better, because C++ is really a pain in the ass to reverse. I don't know if anyone else realizes that. Static tools are just not good enough right now. We need dynamic tools to help us out. And this is a work in progress tool. I submitted it as a work in progress talk. The tool's not done. I'll show you what I have so far, and it's really a collection of tools. So I'm going to release the code after the presentation, and you guys can play with it and send me bug reports or feature requests or, hey, you're an idiot. The number one thing is finding bugs is awesome. I have a lot of fun doing it. I don't know why you're here or why you do it, but that's sort of the focus of the talk and the focus of the tool. Helping you understand the code to be able to find bugs and find logic errors. Yeah. So here's how I go about finding bugs. I go and read the PDF specification, and I say, hey, wow, this little bit here is probably never used by anyone outside of Adobe, and anyone that generates PDFs isn't generating them with anything but the Adobe tool for this little tiny section of the PDF. And I say, you know, I bet they made a few errors in the parsing of this or in the handling of how they're going to display this. So that's step one and step two. And then early on in my career, I would fuzz. So after that, I just throw things at it, find a sample PDF that had that, and just mutate it until bad things happen. But what I learned after about 4 or 5 months of doing this is all your fuzzers suck. They're going to go into one area. You're going to try and make them better. You might try and do some, even with some feedback fuzzing, you're not going to hit the corners, and you're not going to be able to do the thing that a human could do looking at the code. I think we can agree on that. So what's a better way to go about it? You want to audit the code that actually processes these wacky formats that they have. I'm picking on PDF, but obviously that's not the only thing. There's a lot of file formats that get parsed. And so the goal here is to be able to reverse the code enough that you can actually audit the bits that you're interested in without having to audit the entire big application, because that's a lot. So we have stuff that, it's easy to find the specification most of the time, or you can go, if it's not open, you can probably find it online. Someone's probably already reversed on the wire format, right? Not all the time, but if they haven't, then that's not something I'm really interested in. And then finding the dirty corners. Well, I don't know if anyone's seen my blog entry or has been in the business for more than a year, but differential reversing, where you run multiple inputs through a program and look at the coverage, and then you can diff the coverage and find out what the difference in the inputs were on the coverage. So finding places in the program that process just the part of the format you're interested in. People have been doing this for a long time. So Pedro Amini is always yelling that his process stalker has done this forever with the PyMay, and his is really fast. And then the guys at Dynamics do this now. They just had a blog post. They have some stuff to do it. And then number 3 is what we're going to talk about today, trying to find the code and understand it so we can audit it with some meaning. So the goal. I want a tool to tell me what part of the program processes what part of the input. And I want to understand it not just on the byte level, but more on the logical level. So if I'm parsing HTML, I want to know that, okay, who processes the blink tag? Because I want to kill that, right? So we want to go there, find out which part of the binary actually processes the blink tag, which one parses it, which one uses that parsed data that gets put somewhere, some logical abstract syntax tree, who uses that later to display it. Yeah. And here's the screenshot of the tool so far. So this is IDA, if you haven't seen IDA before. And on the right side is the current version of the way it's displayed. So that's sort of like an abstract syntax tree. And what this is showing is part of Adobe Flash Player parsing the AMF format, which is the serialization over-the-wire format for remoting stuff that they do. It's a good subformat to play with because it's specified in the document, and it's easy to find. So yeah, that's sort of what we'll see at the end today, and that's where we're headed. And this isn't a new concept. I'm not representing it as such. I just haven't seen anything public that actually does it. Peter Banya has the Spider Pig that does very similar stuff, but as far as I know, that's not public. He released a demo and a paper, a really long, really in-depth paper about how he goes about doing the taint tracing, the taint propagation, which is data flow analysis, which we'll get to. But I'm pretty sure the code's not available. So what is BASO4? It's really a collection of tools. We have a fine-grained execution trace collector, which is a bunch of words. It just means record everything that you see that happens. We also have this control dependence analysis, which is a static analysis to find the basic blocks that determine, well, we'll get to it. And then 3 is taint propagation analysis. So taint propagation analysis is just tracking the input through the program, how it moves and where it gets stored along the way. And that's what we're going to use to color our executable, those 2 and 3 together. And then 4 is the IDA plugin, which is just taking that taint information that we've captured in 2 and 3 and making it available to the auditor. So now we're gonna, the whole thing is basically just a demo. We'll go to the slides back and forth between the demo and the slides so we can talk about stuff, but I'm just gonna walk through the current use of the tool because that's really easy. So, any questions so far? I haven't really said all that much, but all right. So the first thing we'll do is we'll look at this, well, actually let's talk about the first part, the execution trace. So what I call the execution trace capture tool is voidness. You feed it a command line, the address of the start function, so which module you want to start tracing, and the offset into that module, and a watch point set, which is optional, but this allows you to extend your trace. So you can say, every time I hit this line, I want to capture these variables, or this memory or this register, and this much memory. And at the end, we're going to have this trace that we can use for post-processing. Some tools will do the taint analysis, like taint check, for example, which is something out of, I guess, Berkeley with Donsong. Taint check does it all in process. So it uses a dynamic binary instrumentation to do the taint propagation while the program's running. They have to do it that way because the goal of taint check was to stop badness. So if someone's trying to use a tainted value as a function pointer, it would nuke it. But for us, we're going to take a whole trace first, and then we're going to post-process that. It makes it a lot easier to debug and reproduce your results, and there's a lot of good things that you get out of just post-processing and trace. So trace collection. You want to execute the program and record process state after each executed instruction. So you want to record everything you can to be able to completely replay the program. That includes registers, debugging events like exceptions, and where the modules are loaded, things like that. The naive way is to just record all the registers and any access memory after each instruction. That's, I mean, just thinking about it makes you cringe. How much would you be spitting to disk doing that? How much time would you spend doing I/O? Now, the guys at MSR came up with, they wrote a really good paper on this. It was the Nirvana project. So they have this reversible debugger. I mean, I guess GDB has something that does this now, but not the same way. The Nirvana project will take an entire trace of a program, and then they have these plugins that allow you to go backwards and forward in the trace to do a debug or to do, I mean, you could write BASO4 on top of that, but it's also good for debugging. So they described their method for doing this. And they maintain a whole shadow copy of memory and registers, and they actually emulate most of the integer instructions along the way. And then before they decide whether or not they're going to write out the new modified registers, the new modified memory, they match it against their shadow copy, which they keep by emulation. So they really reduce how much they write out the disk. Obviously, things can change, like memory can change in another thread, or your emulation could be not perfect, or it could be floating point, which they didn't do. And they also have these like checkpoint points where they'll stop after every 1,000 instructions or so and say, okay, here's all the registers that we have now. Make sure that everything you have matches this. If it doesn't, resync. So the other question, besides just spitting a bunch of things to memory, is how fast is this going to be? Well, obviously it's going to be slow. It's going to be really slow. But depending on how you do it will dictate how slow it is. Idea number one, the simplest thing you can think of is actually attach a debugger in single step. And that's what Ali debug run trace will do. Or I guess, I don't know if it still does that. That's the way it used to do it. I think in 2.0 it actually does something a little smarter. But that's not good. You can't run an interactive program like that with any reality. Idea number two is to modify a system simulator like QEMU to dump trace information, and this is exactly what BitBlaze, which is the Berkeley guys, that's how they record traces. And their tool is called TEMU. You should check it out. That's pretty neat. Idea number three is this dynamic binary instrumentation I was talking about. So dynamic binary instrumentation, in case you're not sure, it's really cool. It's like an x86 to x86 just-in-time compiler that allows you to modify the code as it's going through the compiler. So you can instrument, as each basic block is about to be executed, you get to pass it through, well, not executed. So it'll start out and you'll get a basic block. And if you haven't seen this basic block before, it'll get passed through an instrumentation function that'll allow you to add things like, record that this basic block was hit, for example, for a coverage tool. And then it'll cache that new instrumented basic block to the side. And anytime it hits that block again, it'll execute that without having to redo the instrumentation. You should check out the Dynamo tool. Where is it? Yeah, so the Dynamo paper from HP is awesome. It's a really good paper, and it explains it all in excruciating detail, but it really answers all your questions, and I think it was written really well. It's really cool. So DBI is used by Dan Reynolds' Trace Surfer, who also just takes a whole trace of stuff. His is for virus unpacking, things like that. So Voidness is implemented as a pin tool, which is this DBI. And pin is the Intel DBI tool. Other ones you might have heard of are Dynamo RIO and Valgrind. Valgrind is still, I think, Unix only. So other things about Voidness, other features. I was talking about those custom watch points. This is how we end up implementing the start to the taint. So while we're tracing the data flow through the program, we need to initialize we need to have some origin for saying that something is tainted or is an input value. So instead of using like read or send, read or receive or scanf or something that takes input from the system, you can actually do it on a watch point. So you can do it in the middle of a function. So if you know something's already been processed, unencrypted or decompressed, you can set a watch point there and grab it there instead of having to follow it all the way through the decompression or the decryption. So the other thing it'll do is let you, like I said, start the trace in the middle of the program, and you don't have to take a trace of the entire execution because you might not want all the stuff in the beginning, all the setup from the OS. So okay, the current state is that I don't implement the simulation part that I was talking about that Microsoft had created. I do the caching on the side where you're following the program. So as the program's running, you keep track of the registers, and if a register hasn't changed in between two executions, you don't spit it out, which is really dumb optimization, but you have to do it anyway. And multiple threads are not recorded. They're recorded in separate logs, but there's no sequencing. So there's no way to put them back together right now. I've looked into it a little bit, and that Nirvana paper actually describes how to go about it. So let's look at something. We'll start the demo now. So here's a program we might want to trace. Okay, this is just test 001, and it takes some input on the command line and passes it to a function, and then checks the first 2 bytes of the first argument on the command line. So if the first one is an A, it'll just print 1. And if it's not, then it checks the second one. And if the second character is a B, it'll print 2. Otherwise, it'll print 3. It's a really simple program, just to give an overview of how the tool works. So I think it's already compiled, but I'll make sure. All right. So what we want to do is we want to run this trace capture tool in this. And we're just going to give it AA on the command line, so it falls into this first area right here. But before that, like I said, we have to set those watch points. So what we want to do is we want to mark this. So we want to put a watch point on F and mark A and B as tainted, because that's what we want to follow through the program. So to do that, we're going to open up IDA, which should already be open. Oh. Pretend you don't see that. Okay, there's the test 001 IDB. And we'll go to main here. F, where's main? I'm on a netbook, and I'm not doing so great on it. Okay, here's main. So 2 things we have to capture. One is where we want to start the trace. So we're going to capture this, the address of main, because we'll start capturing at main for this. That's the offset is 41. So where's the Okay. Here's the execution of the voidness trace tool. So we have to execute it through pin, because pin is the DBI that voidness runs under. And we pass it voidness as the tool. And then we say the start module, where we want to start tracing, is this test001.exe. And then the start offset is 11460, which we see here. This was loaded at 400000. And then we pass in the watch point file, which is here, and that specifies where we want to start the taint. So then we have to go into F, because that's where we want to start the taint. Here it is. So here we go. Here's F, and we know that this is the address, and that's what this is here. The second line in the file is the address. The third line is an expression that tells you the address of the taint, and that's going to be the ESP plus 4, because we're starting here before we push on the EBP. And that's going to be A. To get A and B, we make the size of it 8 instead of 4. So here's 8. So that's how we set up our file to run the tool. And here's trace test.bat, which we're going to run now. The startup of a dynamic binary instrumentation tool is actually kind of slow because it has to cache all the things they're going to get. The startup of a tool, of a program, I mean, executes a lot of code only once. So you're going to have to go through that instrumentation step many times, and you're not going to reuse any of the instrumentation things that you've done. So DBI always takes a minute to start up, no matter how small the actual tool. So we're done that, and let's see. Well, I'll show you what we got out of that trace tool. So what did voidness produce? Here is a ASCII version of what it produced, okay? So the image loads up top. It's going to be the standard things you see, kernel DLL, and then the exe, and NTDL. And then it'll say, thread start, and then a bunch of system calls. And then image loads, another thing we record. And then things like the instruction address, and then registers that are, and the value of the registers that have been written or read. So that's, a giant file full of that. And it's not stored like this, but this is just a dump of what it, actually means. It's stored in a very compressed binary format. Okay. Now onto the static analysis. So now we have this trace, and we can't really use the trace yet because we have to do that analysis I was talking about first, which is the control dependence analysis. And what that takes is, and before we can do that, we were going to use IDA to just grab the control flow graphs. So we use an IDC script to grab the control flow graphs and spit those out into a really easy to parse ASCII format. I'm not going to go through that. That's pretty simple. A lot of tools do it. After we have the control flow graphs, we're going to do this control dependency thing that I was talking about. And that's going to spit it back into this analysis DB, so we don't have to compute it every time. So if we're working on the same binary a lot, we'll just do it once, spit it to the database, and then reuse it again. And this is what a lot of the static analysis tools do, like all this dynamic stuff and PageRoom stuff does it too. So let's talk about control dependence. And to talk about control dependence, the way you calculate it is through something called post dominance. And the way you calculate post dominance is by reversing a control flow graph and calculating dominance. So the dominance relation is if X appears on every path from entry to Y, then X dominates Y. It sounds more complex than it is, I think. So, for example, 1 is going to dominate everything in this graph because you have to go through node 1 to get to anything else, right? What about, which nodes dominate 6? Well, 2, 1, and entry, right? 3 and 4 don't dominate 6 because you don't have to go through either one of them to get to 6. Does that make sense? Yeah? Okay. So 1 and 2. And 6 also dominates itself, but we're not gonna care about that. What about 8? Well, the only node that dominates 8 is 1, because everything else is conditional on the branch that 1 takes. So just 1 and 8. Post dominance is calculated, like I said, as the dominance on the reverse control flow graph. And then control dependence is calculated based on that. X is control dependent on Y if Y determines if X executes. It's pretty simple though, right? So, anything in the middle of this graph, so 3 and 4 are controlled, 3 and 4 are control dependent on 2. 2 is the branch that you take that determines whether or not 3 or 4 execute. It's just the one right above on the tree, the nearest sort of branch point. This control dependence is used to be able to match up the taint that you calculate to the instructions that are sort of dependent upon that value. And that's another type of marking that we'll put on our IDA plugin. Taint propagation. So actually, let's do the control flow control dependence execution here. The demo. Okay. Oh yeah. It's already in the database. So we have that done. Now the taint propagation that I keep talking about takes the execution trace and the control dependence relations that we saw, and walks over the entire trace and calculates the flow of the data and writes out this taint info. So here's a sample. If we put a watch point on the call to read U32, such that EAX was marked as tainted after this call returned, then we'd start by, so after the call, EAX would be marked as tainted. Then the add EAX and 0x20 would execute, and still EAX would be tainted because it goes back into EAX. Then there's the load effective of EAX and 4 times EAX, and once again, only EAX remains tainted. We'd push EAX and we'd mark that address on the top of the stack as tainted. Then we would, after the XOR EAX, which is going to clear EAX, we'd clear the taint value on the register X, but the taint would remain on the stack address. Then we'd push this 0 value. Nothing would happen because EAX taint was cleared, and then we'd call function. If function was something we were interested in, we'd see that the first value on the stack was tainted, and we'd follow it through that function. Now, once the taint info is computed, linking the byte offsets from the tainted input to logical chunks is next. This is, let me show you the plugin. It'll be a lot easier to understand, I think. So on the right side, we have this syntax tree, and it's really weak for this example. We only have these 2 values, A and B, and they have no relation to them. But if we click on node A, and then I got to refresh this. There we go. And we can do the graph view. So we can see that A here is, here's the value of A on the stack. And we see it's transferred to EAX. EAX takes goes into another place, a local on the stack. And then the control, the taint gets propagated down this way. And I'll show you how it was calculated over here. Here's the output of that taint analysis tool. Well, the debugging output. Here's where the taint starts. Here's where those watch points I was talking about occur. The ones that we set up on F. When F is entered, we taint 8 bytes here. And so it's A and B on the stack. And then we scroll down here, and we see that at this move it from the stack into EAX, we're going to transfer the taint from the stack to the first byte of the register, from the second byte on the stack to the first byte, to the second byte of the register, and then third byte to the third byte. So we do it byte by byte based. Even though the register is 4 bytes wide, we want to actually trace it on a byte level and not on the word level. And then here's the next part where EAX moves back into the temporary, and we have the moving it from the register into memory. So we move the taint from the register to the memory taint. Here's where we're actually going to taint the flags. So this is where we're comparing it to 40 to A. So this is matched up to this conditional right here. And this is x equivalent to A. And because X is tainted, we're going to taint this conditional on the flags with the taint from A. And then when the jump not 0 is taken, we know that those flags were tainted by that, and we propagate that. And then these marks are all created to, whoops. The marks you see are the taint created by the control dependence relation that we calculated. So we know that this jump not 0, or we know that this block here is control dependent on this jump not 0 block. So that anything that gets executed in here is dependent on the value of A, which we've calculated with the taint propagation. Does this make any sense? I'm sort of just going up here and droning, but yeah. Please ask questions. What's that? Okay. I don't do any. I remove the taint. Yeah, then I say the entire thing is cleared. Yeah, I don't want to overestimate what I think I know about it. You know what I mean? I want to be very conservative. Yeah. And I don't do any bitwise, and I don't even have XOR in right now to do the clear. So in my taint propagation, I don't actually clear. So XOR is a special case. So if XOR EAX is going to clear EAX, and it's a commonly used idiom. So it's something we have to put in to be able to say the taint is cleared from that value. Whereas usually if you XOR EAX with some constant value, you'd say the taint is going to still exist because it's just combining some value with some other value. And if the value was already tainted, we want to leave it tainted. But XOR EAX is one example where you're going to have to clear the taint. Same with like sub EAX. Those are things I don't take into account right now. I only have 15 instructions that I do the taint propagation on right now. There's a open source tool, or I don't even think it's open source yet, a tool that will soon be open source called Dighton from the Georgia Tech people, and Vincenzo Iozzo is actually working on it too. He gave a talk at Black Hat about using it for fuzzing. Dighton, D-Y-T-A-N. It's from, just Google Dighton and Georgia Tech. Anyone have any other questions while we're here? How does it handle a call through a pointer? You do not, so you can't just go tainting everything that comes after that. I've been considering ways to do this because a lot of parsers will have large switch statements, and those switch statements are the jump tables, and to calculate the address for the jump table, you're going to use this tainted value, and you need to say that, okay, this is actually dependent on that. So right now it doesn't exist in my tool. I mean, it'll just not say that's untainted. It won't follow the control dependence. But that's something that I think you'd want to add as a special case, because it's something you'd find quickly in the binary, and you'd want to say that the taint would propagate that way. It just doesn't do it yet. Another thing that I've been thinking about, but that I haven't done yet, is self-modifying code, or like JIT code, because we can't do all the static analysis beforehand. You'd have to record the stuff that gets executed, which you do with the trace tool, and then put it back together and do your analysis afterwards, or just in time itself. You couldn't do it beforehand in the database like I'm currently doing it. Yeah. Well, since you have everything available, it's actually the logical address, so or the virtual address. So if EBP plus 4 equals ESP or whatever, then yeah, it's fine, because it's actually the address, not. Does that answer your question? I think that's what you're asking. I'm not sure. Yeah. Any other questions about this stuff here? Okay. So this, the other cool thing about this is that the nav bar up top will get colored based on where the taint is, so you can quickly jump to where you want to be. And the other thing I'm trying to integrate is what's the Java parser generator called? Can't remember. What is it? Antler. Yeah. Thank you. Antler has a really nice parse tree representation that I'd like to steal from them in their Antler Antler development tool. It draws it really nice and it represents it really well, because the tree I use right now is not optimal. I mean, it doesn't represent both repeatable pieces and a hierarchy, like breaking down an atom into multiple, like a non-terminal into multiple terminals and then non-terminals. But Antler does a really good job with that, and I think that's probably where I'm going to end up, either stealing theirs or making one just like it. If anyone's seen that, I don't know. Okay, where were we? There's something else I wanted to cover. So the whole point of this BASO4 was to eventually get to the point where we could do multiple traces at once, not at once, multiple traces in a row, and then correlate those. So we say that in this trace, this bit of code always parses out the blink tag, but in the second execution, it always parses out the paragraph tag. And so then you know that, okay, what you marked as part of the code that actually processes the blink tag is wrong. And if you run this on, increasingly larger sets of data and increasingly more complex pieces of input, then you'll be able to come up with like a probabilistic coloring of your of the IDA shading. That way you have like a light blue would say like, okay, it might be tainted, we're not sure, and the darker blue would be, okay, in every execution we know that this always processes this type of data, and it's easy to see. That should be not too bad to do, but I haven't done that yet either. And then the other thing is this control dependence data that we have. Right now I'm throwing all the colors, like the taint based on control flow, the taint based on just data being moved, and then things like the guy over here asked about tainting based on indirect jumps. All that sort of gets lumped in together. It'd be nice if you could turn on and off different types of taint and like we were talking about before, add sort of hints, because as you're auditing, you get a better idea of how things are working, and you're a lot smarter than the computer usually, so you can add those there. And I think that's everything I have. Yeah. Yes, right. Yeah, that's not at all. That's right. That's the other thing I want to talk about. Thanks. So you have to write your own parser that will take an input and then give you the byte ranges and match those to the atoms that you're gonna, or the non-terminals and terminals, the pieces of the parse tree that you want to use. That's definitely, that's left up to, the person that's using the tool. And then you have to I have some scripts right now that'll take that and generate the input you need to give the IDA tool to draw the trees, but it's really ugly, and hopefully it'll get better. There are a lot of places to go with this, and I think one thing would be to use the Dighton taint analysis. They've spent a lot more time doing, because x86 is ugly. I mean, anyone that's ever used it for a long period of time, there's a lot of corner cases, a lot of things you have to consider, stuff you have to do, especially when you're doing this taint stuff that I'd probably get wrong. So I'd like to steal that from someone. And then drawing the parse tree I'm really doing it wrong. I really do want to steal that antler stuff, and I think it'll look a lot better in there. Any other questions? Yeah.
When you're running the traces, I would imagine when Ken is doing the instrumentation, it's less slow than when it's actually running through.
That's right. Yeah. I don't have a way to negatively do it. So the way it works now, like I was saying, there's like that start the origin of the trace, right? That actually works on a stack level, because exceptions and things, a lot of parsers use an exception to sort of jump way back out of the parse. And if you don't do that, then you're never going to turn your trace off. So that's what that does. I don't have a way to then prune the tree deeper in there. Like, if you say, oh, you get to this part of the binary, I don't want to look at it. But I think that's not too difficult to do with pin, because I have the tools to do it the other way. But that's interesting. That's a pretty good idea. I haven't gotten that far yet. Any other questions, please? No? All right. Well, yes. Yeah, you said Flare, right? Yeah, that's a really cool tool. That's a little slightly different. So what they do there, I think, correct me if I'm wrong, I know people are here, know about this tool. Flare is an in-memory fuzzer, I believe. And there are two things it does, I think. One is that you're allowed to force certain paths along the binary to try and exercise pieces that are harder to access. What else does it do? I'm trying to remember. I'm not sure. So it's slightly different than this. With Flare, what you're trying to do is exercise other parts of the binary that you're not sure how to get to without actually solving the data flow equation to get it there. It's a cool tool. They did a really good job, but that's slightly different. Any other questions? Questions? All right. Well, I think that's everything I have. You can come up and talk to me if you didn't want to raise your hand, or you can send me an email. I'll go way back up here. And please send me an email if you're interested. I'm going to be releasing all the code on bitbucket.org by the end of the weekend. And play with it. Let me know how it goes. Like I said, and it's obvious, it's really young, but I think it's going to be something useful. Since no one wants to release their code for this, I'm willing to give it a go. Thanks for your time. I hope it wasn't too dry and boring. I don't know how to make this any more interesting. Thanks.